In this video I will talk about the numerical analysis, the Newton's method. I am Asif from Mechanical Design Engineering under National University. This is a course of Advanced Numerical Analysis supervised by Professor C. Joachim. So I will talk about here the numerical method of Newton's, applying the Newton methods of convergence, how it works. I will define its method and explain a demonstrative code in the DIL2 package, which is step number 15, and I will discuss the result at the last of the video. So in the Newton's method, I will discuss about the mathematical viewpoint, terms of the course, and the results. So what is the what about it actually starts from the solver selection. So this is the previous equation, where this is the A, or this is one of the matrix form, which is which is proportional to the UK, and UK is the this derivative. Well, what is UK here? Say for example, if this is an object and we need to converge this object, so then in the numerical analysis it should start from the U, and step by step it should come to the answer. So this is the step, which could be this is the U, total U, and I'm sorry, this is the initial condition, and these are the steps of the UK. So the sparse matrix will be dependent on the UK value. So what would be the solver? In this case the solver is conjugate gradient, because the A is symmetric. Why it's symmetric? Because the derivative of nonlinear, it is a derivative of the nonlinear operator, and also it is positive because in the previous lectures it is declared, it is explained that in this matrix the convex energy function is minimized as much as possible. So now I will talk about the del UK here. So the first condition of the boundary values of the del UK is it must be a constant number. So if the initial condition is u0, which is g, then after derivation it will be the same. So how it is possible? So in this case the initial, this is the zero boundary. So if the term is zero boundary, then the derivative will be also be zero. So this term is totally zero. So in that case this term will be the same constant value. However, how the Newton's method converges? Well, in when we rememorize the concept of numerical method, then we may be introduced about this term UK plus 1, where is UK plus del UK. Well, for the convergence method of the applying a Newton's method, it might not follow always this formula. Why? Because it might follow the relaxing the iteration, and it takes this type of equation where alpha is a coefficient, and with this equation it takes the relaxation for for converging. Well, the algorithm for alpha k, it depends on the actually the value from 0 to 1. So if it's is equal to 1, then it might be quadratic convergence, and if it's less than the 1, then it will go slow. That means if it is the solution, we want to make a convergence here. So if the numerical start point is here, then it will go very slow to convert, And what about this one? For it may not converge for alpha k is equal to 1, but for frequent convergence it must be -1. But yeah, it also depends on the residual function, which is can be declared like that. And you know how this is the condition. If the condition follows like this, then it would be regarded as alpha k. If it doesn't follow this condition, then it might be taken as alpha k by 2 and try it again and again. And after that, when this conditional is fulfilled, then it will compute this equation. So actually for simplicity always alpha k is regarded as 0.1. Okay, and what about the wave convergence? What is the problem of the convergence? I will show it here. Say for example, if we have this point and the point starts from here, it might continue looping here or go from this point or wander around this area, so it might not converge. Okay, so it's for converging, actually the coefficient of the alpha I'm sorry, it has, so in the Newtonian method, if it starts from a very far away from the result to convert, then it might be looped here or go from other places like that. So actually for Newton method, it has a radius for convergence. Say for example, if it starts here and it want to converge this point, then it has a radius. So the radius is proportional to the second derivative divided by the third derivative. So the large derivative with nonlinear problem, for that case the radius will be very small, which is very too much small. So in that case the convergence will be very short, very small. Okay, and for that's why since it doesn't work like uk is equal to uk plus 1 here, uk plus del uk, it always doesn't work like that. So how can we get the very a point which is placed very a far distance? Okay, so it will not come here with one step, rather it will come here with a frequential step or frequent step, which is determined by the alpha k that I have talked about in this page. So what are the implementation of that? So for making a mesh, it will make a coarse mesh and do the iteration, and will check while iteration it will check the condition of the residual and save the solution for the current mesh, and then refine the mesh step by step, and then it will go for the second one. So we can be introduce the solver selections methodology and the conditionals here, and I will talk about the course now. So let's take a look with code. I will go to the DIL2 website, then go to the tutorials. I will find out the 15, step number 15 here. Now there is the 15, nonlinear elliptic problem by Newtonian method. If I go here, then I would like to go to the result first. these are the outputs. So this is solved on a circle. The boundary value was signed in the down, up and down manner. So this is the coarsest possible mesh here also. This is the more and more refined final edge. It looks like this. This is hard to see, but you can find the edges here too. Okay, let's show the program. Let's go to the downward. It is quite similar to step 6 here. I can basically look like this step 6. There is a function about the boundary values. I will search for that. So you can see the sparse matrix, and also here the residual constant, which will define the alpha here, and the determine step location and the refinement cycle. Here are the member function. These are the member functions here. The variable which will keep track the current solutions, and it will keep the neutron update, and this is the system for the residual. Then I will go to the bottom of the program. This is the int main. This is the instance of the program. This will be run. Let's go to the run option. We will first create a mesh here. We can see that function for mesh generation, and if we go to the upper one, then we can get the output which will be printed here. And let's go to the upper. Here are the places where the equations are being solved. And these are the boundary conditions where it is limited by the template dim. If it's 2, then it will give us the 2D, and if it's 3, then it will give us the 3D. And what about the surface problem? The surface problem is related with the refined mesh, where the estimated error parcels are defined here, and if we go to that surface problem, we can get the residual systems, and this is the 10 to the minus 6 here. And if we go up, we can get the finite element parcel and the sparse matrix, definition of sparse matrix here. And here the degree of freedoms tracking is defined here with the FEMLs. So basically I have run the code in my Ubuntu system, but it took almost more than 24 hours, so I have stopped it. If it is run successfully, then we will get the results totally like this. So which portion can we change here? let's talk about that. If we change, yeah. mm, Now we can change actually the output of the solutions, and also the refinement of cycles, and the refine globals. If we change the refine global here, then the meshes will be changed. So yeah, and also if these conditions can be changed according to the boundary conditions, then it will provide us the different results. Thank you.